Welcome to part 1 on rational functions. In this section, our objectives are to identify rational functions and then to be able to graph those functions confidently. The definition for a rational function is a function of the form r of x equals p of x over q of x, where p and q are polynomial functions, and the denominator's function, or polynomial, does not equal 0. So we have to restrict the domain of a rational function to the set of all real numbers except those that make the polynomial equal 0 in the denominator. Let's take a look at f of x as our first example, where we have f of x equals x over x squared minus 9. We need to find the domain, so we ask ourselves, what would make x squared minus 9 equal 0? X squared equals 9 means that x equals plus or minus 3. When x equals plus or minus 3 in this rational function, you will get undefined outputs, or it won't exist at those two values. So we say that our domain is all real numbers except for plus or minus 3. So we'll work our way from left to right. Negative 3 is smaller than positive 3. So we have negative infinity up to negative 3, not including negative 3, union negative 3 to 3, close parenthesis, union open parenthesis, 3 to infinity. Notice I have included all values except for the restrictions on my domain. The restrictions on my domain are only plus or minus 3. There are vertical asymptotes at these values. Let's take a look at example 2. We need to use division and shifts to graph f of x equals 3x plus 5 over x plus 2. Now, my favorite way of doing this is to look at the roots in the numerator. So I'll have 3x plus 5. If I set that equal to 0, I will get a root. The root will be at negative 5/3. If I set the denominator equal to 0, I will have x plus 2 is equal to 0. So x equals negative 2. And I know that this will be a vertical asymptote at negative 2 because this is where the denominator equals 0. So I'm drawing a dotted vertical line at x equals negative 2. Now if I look at, so right about here, I will have a 0 of the rational function. Now here's something I haven't talked about too much yet. If the leading coefficients degree matches, so both of these are 1, then there is a horizontal asymptote at the value of the 3 over 1. So there is a horizontal asymptote at 1, 2, 3. So we now have enough information to get a general idea of what this graph is going to look like. Let's pick a test value to the left of negative 2. Let's say negative 3. And let's also pick a test value to the right of 0. Let's say it's 1. This will tell us where our graph exists. At negative 3, we would have negative 9 plus 5, which is a negative value, over negative 3 plus 3 would be negative. So this is overall a positive region. Now let's take a look at anything greater than or equal to 1. If I put 1 in, I will have 3 plus 5, which is positive, over 1 plus 2, which is 3, which is positive. So this is a positive region. I know that the curve must be positive and hug an asymptote to infinity. I also know that to the left of the asymptote, I must have values for my function that hug asymptotes and are positive. To the right of the vertical asymptote, I know that the function must cross into positive territory, and so there is only one way this function can exist. It must cross the root, but it cannot cross the vertical asymptote. It also must hug the horizontal asymptote to infinity. The function to the left of -2 must be positive, and it also must hug the vertical and horizontal asymptotes to infinity respectively, and so it must exist in this region here. So the things to remember as you move forward with rational functions are as follows. Figure out where your vertical asymptotes will be. Check to see if you have any horizontal asymptotes based on the degree of the leading terms in the numerator and denominator. Pick test values to see where your positive and negative region might exist, and always cross the root defined by the numerator.